In Robotics 1, we learned a little bit about DC motors. We learned that a DC motor takes a voltage as an input and produces velocity as an output. It makes this conversion via an equation that is called the motor equation. The motor equation tells us that the velocity of the motor is proportional to the voltage input. For this reason, DC motors are very useful as robot joints if we're trying to control the velocity of the joints. But the DC motors are not very useful if we're trying to control the positions. In order to control the positions of the joints, we often use a device called a servo motor. A servo motor has an integrated sensor that reads the position of the DC motor. In order to show that my sensor is reading not the velocity but the position, I'm going to put an integrator, which is typically represented by a block that says 1 over s, in between the velocity and the sensor. This entire device that includes the DC motor and the sensor together is called a servo motor. So a servo motor is a motor that controls position by having a DC motor and a sensor integrated together in one device. The servo motor controls position by using feedback control. Today, we're going to be learning about another kind of a motor called a stepper motor that is also capable of controlling the positions of the robot joints. However, in contrast with a servo motor, the stepper motor achieves its position control with open loop rather than feedback control. Controlling positions using open loop rather than feedback control has some pros and some cons. For example, open loop position control done by steppers requires no sensor, while the feedback control as done by a servo does require a sensor. For this reason, steppers are often cheaper than servos, all else being equal. For example, a stepper and a servo of the same torque or the same precision, the stepper motor will generally be cheaper because it does not require a sensor. The stepper motor is sort of a kind of digital actuator, while a servo is sort of a kind of analog actuator. What I mean by this is that steppers are only able to move to certain specified positions, while a servo can move to any position. That means that in some cases, the feedback servo will be more accurate than the open loop stepper motor. Finally, the stepper motor, because it has no feedback, does not have the ability to reject disturbances, while the servo can reject disturbances. I'm showing here a picture of the stepper motors that we use in class. I want to point out a couple of features of the outside of the stepper motor. First of all, one way you can always tell the difference between a stepper motor and some other type of motor is if you grab the shaft with your hand and attempt to rotate the shaft, you will feel a sort of clicking feeling and hear a little bit of a clicking noise as the shaft rotates. The reason for this will become clear when I show you the inside of the stepper motor. Secondly, notice how many wires we have coming from the stepper motor. The stepper motors that we use in class have 6 wires. This is as opposed to the DC motors, which have 2 wires, and the servos that we use in class have 3 wires, one for power, one for ground, and a signal wire. A stepper motor will always have more wires than the other types of motors. Sometimes they have 4 wires, sometimes 6, sometimes as many as 8. And once again, you'll see why that is when we look at the inside of the stepper motor and take a look at how it works. So here I'm showing the inside of the stepper motor. Like other motors, stepper motors have a rotor attached to the shaft and a stator, which you see over here. The rotor and the stator of a stepper motor have some unique features. The stator consists of a number of poles, which you see here as wire windings. And these poles are all arranged in a circle. Each pole consists of a coil of wire, and also, I don't know if you can see it very well here, we'll get a closer up look in a moment. It also consists of a number of ridges attached to this coil of wire. You can also see on the rotor part, if you look closely, that there are a number of ridges on this circular rotating part. It's these ridges that allow us to control the position of a stepper motor. To help explain what these ridges are all about, I'm going to show you a little bit closer view of the rotor. Here's a closer picture of the rotor where you can better see these ridges that kind of look like gear teeth. And notice that there are 2 sets of these ridges right next to each other. If you look closely at these 2 sets of what look like gear teeth, you'll notice that the teeth on the top disc do not line up with the teeth on the bottom disc. That's actually a very important point to note in understanding how a stepper motor works. These 2 discs are attached to each other so that the 2 discs rotate simultaneously. Now, although these ridges look like gear teeth, they're not actually gears at all. And although there are similar ridges on the stator, these teeth on the rotor do not ever physically make contact with the teeth on the stator. Instead, the stepper motor uses the power of magnetism to cause the rotor to rotate relative to the stator. The gear teeth on the bottom disc will be magnetized as a south pole, and the teeth on the top disc will be magnetized as a north pole. Let's take a look now at the rotor and the stator of the stepper motor from a top view. I'm going to show a diagram of this. Here's a diagram showing the rotor and the stator of the stepper motor from the top view. In this picture, red represents the North Pole and blue represents the South Pole of the magnet. And so in this disc, which represents the rotor, you notice that the North and South Pole individual gear teeth alternate. That's because the North Pole disc of the rotor is positioned on top of the South Pole disc of the rotor, and those 2 discs are not lined up. That's how we get an alternating North and South Pole in these individual teeth. So in this picture, the North Pole is shown as red and the South Pole is shown as blue. Now, when we put a current across one of these coils, which is shown here as these T-shaped parts, The pole that we put the current through is magnetized. The part of the pole that has the little gear teeth, shown here, is magnetized as a south pole. When the pole is energized and hence magnetized, the same pole teeth in the rotor are repelled and the opposite pole teeth in the rotor are attracted. You see in this picture how the north pole teeth, shown in red, have lined up with the south pole teeth in the pole. Note that in this picture, the two poles, which are colored red and blue, have current going through the coil, while the other poles do not have any current going through them. Now consider what happens when we turn off the pole that is currently on and we turn on the next pole. Notice how the red or north pole teeth on the rotor are not currently lined up with the teeth on this pole and this one. When we remove the current from the poles that are currently energized and apply current to this pole and this one, the disc will rotate a distance equal to half the thickness of one of these teeth, so that the red north pole teeth will line up with the now energized pole, which becomes a south pole. The way we get a stepper motor to rotate in a continuous fashion is by turning on and off the poles in order. If I turn the poles on in order in a clockwise order, then the disc in the center will rotate clockwise. If I turn the poles on and off in a counterclockwise order, the rotor, the disc in the center, will turn counterclockwise. Each time we energize the next pole in sequence, the disc will rotate a set amount, and the distance that it rotates is equal to 1/2 the thickness of one of these gear teeth that's on the rotor. This is the distance that the shaft rotates per step. This is why a stepper motor is called a stepper motor. Each time the rotor moves the distance equal to 1/2 the thickness of a tooth, we say that the motor has moved one step. Here's an animation showing a stepper motor working. As you watch this animation, try and focus your eyes on just one pole and watch what happens to the teeth on the rotor as that one pole is energized. So, how can we control the position of a stepper motor? For the stepper motors that we'll be using in class, we know that there are 100 teeth in the rotor. There are 50 teeth in the north pole disc and 50 teeth in the south pole disc. Let's take a look at the bottom of the stepper motor casing. It's very difficult to see here because the resolution of this photo wasn't very good, but right here on the casing it says 1.8 degrees per step. Does 1.8 degrees per step make sense with our knowledge that there are 100 teeth in the rotor? We know that there are 360 degrees per revolution. And if we divide that into 100 teeth per revolution, we get 3.6 degrees per tooth. We know that the distance that the rotor rotates at each step is equal to 1/2 of a tooth. So we then multiply this number by 1/2 tooth per step, and that gives us 1.8 degrees per step. Let's look back briefly at the inside of this stepper motor. Remember I said that our stepper motor has 6 wires. 4 of those wires go to the coils in the motor. One of the wires energizes this pole, that is, it sends current to both of these coils of wire at the same time. The next wire is connected to these 2 coils simultaneously. The third wire is connected to these 2 coils, and the fourth wire is connected to these 2 coils. The remaining 2 wires are both for ground. Note that although a stepper motor is very good at setting position, it can also be used for velocity control. We control the velocity of a stepper motor by controlling the speed at which we energize the coil. If we can precisely time the amount of delay between energizing one pole and energizing the next pole, we can control not only the position but also the speed of the stepper motor. In class, we'll be doing a lab where we learn to set both the position and the speed of a stepper motor. Let's look at a brief example for how we set the position and the velocity of a stepper motor. To begin with, let's suppose that you have a stepper motor that says in its documentation that it has 1.8 degrees per step. Let's suppose that you know that you want to set the motor to a 90-degree position. We set the position of the stepper motor by counting steps. We divide the 90-degree position target by the 1.8 degrees per step, telling us that we need to move the stepper motor a total of 50 steps. We would then program our microcontroller to energize the poles in sequence, counting out 50 individual steps. As we do this, we have to assume that the stepper motor always makes a step when we energize the next pole. Sometimes this is not the case. A stepper motor might be subject to an error of missing steps. When a stepper motor misses steps, we think that it has moved a certain distance, but it has not moved the correct distance. In this case, our microcontroller is not aware that steps have been missed, and so positioning error can be induced. This is one of the drawbacks to using a stepper motor as opposed to a servo motor. The servo motor, which has an integrated sensor, would be aware that the motor has missed a step or not gone the correct distance and would be able to compensate. The stepper motor, on the other hand, when it misses a step, it is not aware that it has missed a step. However, the simplicity of this equation is one of the reasons that stepper motors are so popular. It's very easy to figure out how many steps need to be commanded in order to get the motor to go to a particular position. Now, let's take a look at stepper motor velocity. Suppose that we have a motor with 1.8 degrees per step. And suppose that we want to set a motor velocity of 1000 RPM. We need to figure out how long in milliseconds each pulse should be on. We can answer this question simply as a unit conversion problem. Recognize that what we're looking for, how long each pulse should be on, is an answer in units of milliseconds per pulse, or milliseconds per step. A pulse and a step here is the same thing because one pulse of electricity causes the rotor to rotate one step. Let's start out with our desired speed, 1,000 revolutions per minute. I need to convert revolutions to steps, and I need to convert minutes to milliseconds. I'll start with the milliseconds. We have 1 minute per 60 seconds, and we have 1 second per 1,000 milliseconds. That will give us the millisecond unit that we're looking for. Now let's convert revolutions to steps. I have information on the number of degrees per step, so I'm going to first convert my revolutions to degrees. We know that we have 360 degrees per 1 revolution. And I'm told that my motor is 1.8 degrees per step. So 1 step is equal to 1.8 degrees. Revolutions cancel and degrees cancel, leaving me with a number that is steps per millisecond. When I do this calculation, I find that I have approximately 3.33 steps per millisecond. I simply invert that answer to find that we get approximately 0.3 milliseconds per step. This answer is useful for me when I'm trying to set the speed of a stepper motor with my microcontroller. This number tells me how many milliseconds I need to wait between turning on one pulse and turning on the next pulse.